Sorry. I forgot to turn on this thing. Okay. So here, yesterday we did the second law. In second law, we discussed that the line joining the planet to the sun sweeps equal area in equal intervals of a time, that is aerial velocity dA by dt. This dA by dt is the aerial velocity, remains constant. So here the planets which are moving around the sun, C is a sun I took here, and the sun as a focus, and all the planets are revolving around that. So area swept by the planet to move from Q to P is nothing but delta theta or d theta. Okay, and this is a position vector r, and planets are having the mass small m. Okay, and area swept by the planets dA is equal to half r square d theta. Then I multiplied numerator and denominator by m. Then after that I divided by delta t on both the sides. Okay, and we have inertia I is nothing but mr square, and d theta. Okay, d theta by dt. We did at the third chapter. D theta by dt is nothing but what? Angular velocity omega, because delta theta is the angular displacement. Okay, so we are writing d omega, and then this is the aerial velocity, so we can write dA by dt is nothing but half mr square is nothing but I upon m, and d by d theta is nothing but omega. Okay, and here after this we know this also, I omega is nothing but what? L is nothing but I omega. So we can write here dA by dt is equal to half L half L upon m, or we can write L upon twice m is nothing but what? Your aerial velocity, and that should be constant throughout the rotation. So L is nothing but, we know that, angular momentum. Okay, so since gravitational force is a conservative, so central force, angular momentum, L remains conserved. That's what dA by dt is also what? Remains constant. So this is the proof for the second law of area of the different laws. So first, this is a proof for the second law. Okay, so Kepler's second law is proved here for planetary motion. So those who want, they can take the expression, or they can take a screenshot of this. Then we'll go for the derivation for the third law of periods. Okay. Take a screenshot. Okay, chalo. Okay, chalo. Now we'll go for third law of periods. So yesterday I explained you law of periods. Okay, the square of the time period is directly proportional to the radius cube. Okay, this is t square is directly proportional to the cube of the given radius. So again, I hope everyone took this. Now we have to prove t square is directly proportional to r cube. Okay, तो अभी क्या करना है? How to find out this expression t square is directly proportional to r cube. So again we have to consider a planet. Okay, suppose here this is the elliptical orbits are there. Okay, this is, you can take this as a sun, and other planets are revolving around the sun, and the planets are having mass small m, and capital M is the mass of the sun. Okay, and the radius of this elliptical orbit is capital R. Okay, so here, of course, as the planets are revolving around the sun, that means there is what? Centripetal force is also responsible. Okay, and as they are maintaining the distances between them, that means no planets are attracted towards the sun. Okay, without any disturbance, they are rotating in the spherical or elliptical orbit. So here gravitational force is also acting over here. Okay, so yesterday we did this gravitational force. Fg is nothing but we got G Now here it will come capital M small m upon r square, and centripetal force is nothing but we have mv square upon r square. Can you getting this? Okay. So these are the two forces are responsible. Centripetal force is responsible for the rotation, and there is a gravitational force between these two bodies. But both are forces only, so these two forces we can compare, and we can write here Gm m upon r square is equal to mv square upon r square. Okay, so this is nothing but what? Gravitational force is mv square by r. mv square by r. Small m is get cancelled. 1r and this r is get cancelled, and we will get v square is equal to gm upon r. Okay, this is what the velocity we are getting. Okay, and we know that v is nothing but small r omega, but here I will take it as a capital R omega because the radius of that elliptical orbit is capital R. Okay, v is nothing but r omega. Then substitute the value of v over here. So r omega whole bracket square is nothing but gm upon r square. Okay, so once you get this, then obtain the value for gm. Okay, so gm is nothing but you can take this r square transpose over here r square, then this square of r omega square, then again square it, and here omega square. Okay, so you will get here sorry, not r, so this is r, no? Yeah, r will go here, so you will get r into r square. So powers are get added, 1 plus 2 is a 3, so 3 omega square equal to gm. Now how to solve this? Okay, what we want to prove this t square directly proportional to r cube. By not r cube, but how the t we can replace. We know that omega is nothing but 2 pi into f or 2 pi by t. Okay, so you can take the value of omega, angular velocity is nothing but 2 pi by t, and substitute the value over there. Okay, so here if we substitute omega value, r square, omega is nothing but 2 pi by t, and we are making a square of this, so r square into 4 pi square upon t square. This is nothing but gm. Okay, now we have to transpose that t square. Okay, just check how I am solving here now, and t transpose to this side, t square is equal to r cube. Yeah, r cube into we have 4 pi square, and this gm also I transpose to this side. Okay, so here t square is equal to r cube, and if we take 4 pi square by gm, value, gravitational value is also constant, mass of the sun is also constant, and 4 pi is also constant. Okay, so we can take this as a k, and from this we can write t square is directly proportional to r cube. Okay, so this is the derivation we have for the third law of periods. Okay, for planetary motion. So this is the derivation. Getting this? So take a screenshot of this. Finished? Everyone copied? Okay, chalo. We'll go for the next derivation, that is escape velocity. Okay, yesterday we did some derivations. Okay, I hope you remember all the derivations. Okay, so here escape velocity is nothing but what? The minimum velocity. Escape velocity is nothing but a minimum velocity which we require, or that satellite require, or that body required, okay, so that it escapes from the gravitational pull of the gravitational pull, that is called as a escape velocity. Okay, so give the heading escape velocity. Escape velocity. Okay, so here we are providing some velocity to the object, so that that object minimum speed or minimum velocity which we are providing to this body, so that that body escapes from the gravitational field. Okay, so that speed or that velocity is called as a escape velocity. Again here we are taking one here surface of the earth, we have here mass of the earth m and radius of the earth small r, and the mass of the body is small m. Okay, so here we have these all things, and escape velocity we are denoting by letter v to the base e. Okay, so according to the law of conservation of energy, so total energy on the surface and total energy at some infinite distance are always equal. Okay, so we can write here total energy at the surface. Check what I am saying, or on the surface, or total energy on total energy at infinite or at infinity, both are what same, because energy remains conserved, that will not be destroyed. Okay, so we know that total energy at the infinity, we don't know about that, so we are taking that as a 0, and total energy is nothing but what, kinetic energy plus potential energy. This we know that. And now kinetic energy, we know that that is nothing but half mv square, and potential energy when the mass of the body or that body is on the surface of the earth, because this total energy on the surface of the earth, and in last session we did the potential energy at the surface is nothing but, we got it as a gmm upon, we have r. Okay, capital R, we found this. Okay, then potential energy, no, so potential energy with negative sign we got, and this is equal to what, 0. Okay, so here this velocity is nothing but, we can consider as escape velocity, and now this minus plus is minus, so transpose this potential energy to that side. So half mve square is nothing but gmm upon r, so minus will get plus. Okay, and we are interested in escape velocity, so all the terms like m and 2 I transpose, so ve square, 2 is divided, transpose that, it is get multiplied. Okay, divided by, we can write m into r. Okay, so m and m is get cancelled here. Okay, and ve is nothing but ve square is nothing but twice gm by r, and if you take a square root on both the sides, okay, you will get the answer 2gm upon r. This is nothing but what, escape velocity. Okay, and we know that acceleration due to gravity small g is nothing but gm upon, we have r square. Okay, so we have here r square, so we can write gm is equal to gr square. So if you substitute the value of gm in this equation, ve is equal to square root of 2gm. Gm is nothing but here gr square upon r, so this r and this r is get cancelled, and ve is nothing but twice g into r. So this is nothing but escape velocity. Okay, this is nothing but what, your escape velocity, and this escape velocity is independent of the mass of the object, because there is a no m term is there in the equation, so that's what it is, independent of the mass. Okay, so take a screenshot of this. Finished? Okay. Okay, then we will go for the next derivation, that is orbital velocity. And orbital velocity we are denoting as a v naught, and escape velocity we are denoted as a ve. Okay, now we are discussing about the orbital velocity. Orbital velocity, this is also very important point from the point of exam. Okay, so orbital velocity is the velocity that should be imparted to the satellite so that it can describe the circular orbit around the earth. Okay, at the predetermined height is called orbital velocity. Okay, so whenever we are providing minimum velocity to the body or to the satellite, it can escape from the gravitational pull, and then after escaping they are what, traveling with certain speed. Okay, so that is nothing but orbital velocity. They are traveling around the planets, okay, and around the sun with certain velocity. That velocity is called as what, orbital velocity. Okay, again we can consider the mass of the body or satellite as a small m, and that is revolving around the earth at a predetermined height h. Okay, above the surface of the earth, let v naught be the orbital velocity, and m is what, mass of the earth, r is nothing but a radius of the earth. So suppose we have here, this is the earth having mass m, radius is r, and the mass of the body is m, and it is revolving with certain orbital velocity v naught. Okay, and it is at certain height h from the surface of the earth h. Okay, so here, now here as the body is revolving around the earth, okay, so there is what, centripetal force as well as gravitational force, both are active. Okay, and both the forces are there, so they are similar. So if gravitational force in this case is nothing but g m upon, it is revolving around the surface of the earth due to at the predetermined height h. So this will become r plus h whole bracket square, and centripetal force mv square upon r. You can take this as a r, but this is also r plus h. Okay, so this v naught, v square, you can take it as a orbital velocity, mass, and this masses get cancelled. R plus h and 1 r plus h is get cancelled. So v naught square is equal to gm upon r plus h. Okay, this is nothing but what, the orbital velocity. And orbital velocity, if you take a square root on both the sides, you will get gm upon r plus h. Getting this? So as just now we did here, gm, value of gm we calculated, no, just now. What is the value of the gm here? Gm is nothing but, we have g into r square. Okay, we have g into r square. So I will substitute the value over here, g into r square upon r plus h. So you can take r out. Okay, and you can write it like this also, g square root of, sorry, not g, r square root of g upon r plus h. Okay, so this is also orbital velocity. And one more thing, whenever the satellite is very close to the surface of the earth, okay, so in that case we are writing RH is approximately equal to what, r. Okay, so in that case this v naught will become g r square, this h will become 0, this is r. So 1r and 1r is get cancelled, and we will get the expression g into r. Okay, this is nothing but orbital velocity. Okay, getting this? समझ में आ रहा है सबको? Okay, So take a screenshot, then we can discuss about the relation between the escape velocity and the orbital velocity. Okay, copy this. Take a screenshot. Yasir, are you there? Mohammed, Rujul, Krishna, Indivar, you all are there? Who all are there? Yes, Rujul, Mohammed is there, and Krishna, are you there? Indivar is not there. Huh? Okay. There will be a test on Thursday on work, power and energy. Okay. I already messaged on the group. People are not wrote the exam on waves. So check when you will come and write. Okay, chalo. We'll go for the relation between the orbital velocity and escape velocity. Okay, so if we take the orbital velocity v naught as a g into r, and escape velocity we got it as twice g into r. Okay, so if we take a ratio vo by ve is nothing but g into r and square root of 2 into g into r. So it is gr and gr, the root is get cancelled and we will get 1 by root 2. Or we can write v naught is equal to 1 by 1 by root 2 times of ve, or we can say that here ve is nothing but root 2 times of orbital velocity. Okay, this is what the relation we have. Okay, so note it down. Sometime this kind of expression they will ask in MCQ. Okay. Okay, everyone copied, no? Chalo. Now give the next heading, total energy of the satellite. Total energy of the satellite. What is the total energy? Total energy is again kinetic energy plus potential energy. Okay, so here we can write total energy, expression for total energy. Okay, so we can start with kinetic energy first. Kinetic energy is nothing but half mv square, but we are taking this as a orbital velocity v naught. Okay, so here we can write orbital velocity v naught is nothing but square root of gm upon r plus h. Just now we derived this expression. Okay, so we can put or substitute the value over here, then half m, this value you can substitute gm upon r plus h whole bracket square. This square and this root is what get cancelled. So after cancellation we will get half gmm upon r plus h. We are getting this expression for a kinetic energy. Okay, can you getting this? We just got the value for kinetic energy, half gmm upon r plus h. Okay, and yesterday we did the gravitational potential energy, or potential energy is nothing but minus gmm upon r plus h. This expression yesterday we derived, okay, because we are bringing the body from infinite to some predetermined distance. So we are performing some work done, and that work done we are expressing in terms of potential energy, that is minus gmm upon r square. Okay, so now we can write here total energy. Okay, once you got the kinetic energy and potential energy, then go for total energy, that is nothing but kinetic energy plus potential energy. So kinetic energy is nothing but gmm upon 2 r plus h, and here potential energy is nothing but plus, but here we have minus gmm upon r plus h. Okay, so here minus plus is minus, so I will write here minus. Now if I take gmm common, upon r plus h is also common, so what will remain here? 1 by 2 minus 1. Okay, so this portion will remain here, and total energy we are getting it as a minus half, means here 1 by 2 minus half is nothing but minus gmm upon r plus h. Okay, this is the total energy we are getting this derivation. Okay, and we have here total energy is equal to, we have one relation, total energy is equal to minus kinetic energy, and here we have the total energy is equal to half of the potential energy. Okay, and we can say that here PE is nothing but twice the TE. So from this only we derive this expression. So these are the very important expression, because we are using this expression to find out the numericals or to calculate the numericals. Okay, write down this. I hope I cover almost all the theory for this chapter. Okay. So write down one question. Write down the question. You first take the screenshot. Okay. After taking screenshot, then write down the question. The total energy of a satellite is minus 100 joule. The total energy of a satellite is minus 100 joule. Calculate its kinetic energy and potential energy. Calculate its kinetic energy and potential energy. Okay, I will repeat once again. The total energy of a satellite is minus 100 joule. Calculate its kinetic energy and potential energy. So just now we calculated the total energy expression, as well as we did one derivation also, means we find out the relation between the potential, total energy, kinetic energy and potential energy. So here in this problem, total energy is given. Okay, so here total energy is nothing but minus 100 joule. They are asking us to find out kinetic energy and potential energy. Okay, we have to calculate. We know that total energy is nothing but minus kinetic energy. So total energy I have here minus 100 joule minus kinetic energy. Minus get cancelled, and kinetic energy I got it as 100 joule. So energy unit is joule. So this I got kinetic energy. Now calculate the potential energy. So potential energy I know twice the total energy. Okay, so 2 into total energy is nothing but 100 joule. So that is nothing but minus 200 joule is nothing but your potential energy. Okay, so this kind of questions sometimes they ask. I hope everyone understood this. Very simple and easy problems. Okay, finished, copied everyone. Yes, I'm leaving, man. Write down one more problem and then I'll stop. Write down two planets are having their radius. Two planets are having their radius in the ratio 2:3. Their radius in the ratio 2:3. Compare their escape velocities. Compare their escape velocities. I'll repeat. The planets are having their radius in the ratio 2:3. Compare their escape velocities. Okay, so we have to compare their escape velocities here. So very simple expressions. We can use the final expression, okay, for getting this answer. Okay, and just now we did the escape velocity VE is nothing but twice g into r. Okay, this expression we got. So according to this question, there are two planets and having their ratios 2:3. Okay, R1 is to R2 is nothing but 2:3. Okay, so suppose this is a escape velocity for first body, so its radius is R1, and VE2 is nothing but twice g into R2. So you take a ratio of both of these, twice g into R1 upon twice g into R2. 2g get cancelled, and here you will get R1 by R2, that is nothing but 2 by 3. So we will get the velocities root 3 by root 2, that is equal to root 2 is to root 3. So this is nothing but what? The answer for this question. Getting? So compare their escape velocities, and escape velocities are become root 2 is to root 3. Okay, check what they are asking. If suppose they are asking 2 to 1, then it will come root 3 to root 2. Everyone is getting up to here. So start preparing this chapter also. Okay, so maybe next week Sunday only I am keeping the test on this. Okay, so tomorrow also we have a extra session. Tomorrow I will send you the link accordingly. Okay, I will end this session today. Thank you for joining.